The Big Bang is supposed to be the beginning of everything. Not just the beginning of stars, galaxies, or matter as we know it. The beginning of space, the beginning of time, the beginning of the stage itself. So the first question almost everyone asks sounds simple enough. What was there before it?
And this is where cosmology gets strange fast, because according to some of the best physics we have, that question may not have an answer in the way we mean it. Not because scientists are hiding one, not because the universe is mystical, because the word before may stop making physical sense at the very place we are trying to use it. But if that is true, then another question appears immediately. Why do so many serious physicists still spend their careers trying to push past the Big Bang? Why are there models of cosmic bounces, quantum beginnings, inflationary backgrounds, and even entire frameworks where our universe is only one local episode inside something larger? To answer that, you have to separate two ideas people constantly blur together. The Big Bang as the hot, dense, early universe we can actually model, and the Big Bang as the absolute beginning of reality itself. Those are not automatically the same thing. This is not just a trivia question about ancient cosmic history. It is a question about whether time is fundamental, whether space had to emerge from something deeper, and whether the universe is a one-time event or one phase in a larger process. If our usual ideas of cause, sequence, and beginnings fail at the origin of the universe, then reality is built on stranger rules than our everyday intuition ever prepared us for. The Big Bang was not an explosion into empty space. There was no central point sitting inside a giant dark room, blasting matter outward like debris from a grenade. In the standard picture, space itself was expanding, everywhere. The universe was once in an extremely hot, dense state, and over time that space stretched, cooled, and allowed structure to form. That is why distant galaxies appear to recede in every direction. It is not because we happen to be near the center of some ancient blast. It is because the fabric between galaxies is expanding. This picture is not hanging on one clue, it rests on several. We see the red shift of distant galaxies, which tells us the universe is expanding. We see the cosmic microwave background, the leftover radiation from the era when the early universe cooled enough for light to travel freely. We see that light elements like hydrogen and helium exist in proportions that fit a hot early origin. And we see tiny irregularities in the early universe that later grew into galaxies, clusters, and the large-scale cosmic web. That is the part cosmology is good at. Very good at. The problem begins when people take that success and extend it one step too far. They assume that because the Big Bang model describes the early universe, it must also tell us what reality was doing at the deepest possible beginning. It does not yet. If you run the universe backward through the equations of general relativity, the cosmos gets smaller, hotter, and denser. Keep going and the math drives you toward a singularity. That word has become famous, but it is often misunderstood. A singularity is not a little glowing seed we have discovered at the bottom of time. It is what happens when the equations start producing infinities and stop delivering a sensible physical description. That distinction matters. When a theory gives you infinity in a situation where you expect real physics, scientists usually do not celebrate that as the final answer. They treat it as a warning light. Something important is missing. And that missing piece is not hard to name. General relativity describes gravity on large scales with stunning success. Quantum mechanics describes the small-scale world with equally stunning success. But the earliest universe forces both domains together under conditions so extreme that neither theory, by itself, should be expected to remain complete. So when people say the Big Bang was the beginning because the equations point to a singularity, the honest response is narrower than that. The equations tell us that our current classical description of the universe cannot be trusted all the way to zero. That is not the same as proving there was nothing before. It is proving that the map tears at the edge. Now the deeper problem. In ordinary life, the word before feels harmless. Breakfast came before class. Yesterday came before today. Causes happen before effects. But that only works because time already exists as a framework in which events can be arranged. Near the Big Bang, that framework may not survive intact. In modern cosmology, time is not just a neutral background clock floating outside the universe. Time is tangled up with the universe itself. It is part of space-time. So if space-time, in the form we understand it, emerges with the early universe, then asking what happened before time may be like asking what is north of the North Pole. The sentence is grammatical. The intuition feels real. But the concept may not map onto anything physical. That is one of the hardest ideas in all of cosmology, because human thinking is built inside sequence. We are temporal creatures. We expect stories to have a scene before scene one. The universe does not owe us that kind of story. Still, physicists keep digging because the question might be ill-posed is not the same as stop investigating. It may simply mean that the right description of the beginning will not look like an earlier moment on a familiar timeline. It may require a different structure entirely. Now, the deeper problem. In ordinary life, the word before feels harmless. Breakfast came before class. Yesterday came before today. Causes happen before effects. But that only works because time already exists as a framework in which events can be arranged. Near the Big Bang, that framework may not survive intact. In modern cosmology, time is not just a neutral background clock floating outside the universe. Time is tangled up with the universe itself. It is part of space-time. So if space-time, in the form we understand it, emerges with the early universe, then asking what happened before time may be like asking what is north of the North Pole. The sentence is grammatical. The intuition feels real, but the concept may not map onto anything physical. That is one of the hardest ideas in all of cosmology, because human thinking is built inside sequence. We are temporal creatures. We expect stories to have a scene before scene one. The universe does not owe us that kind of story. Still, physicists keep digging because the question might be ill-posed is not the same as stop investigating. It may simply mean that the right description of the beginning will not look like an earlier moment on a familiar timeline. It may require a different structure entirely. There is also a sharp line between what we can observe directly and what we infer. We cannot take an ordinary picture of the Big Bang. Light was trapped in the early plasma for hundreds of thousands of years. The oldest light we see directly is the cosmic microwave background, released when the universe became transparent. Everything earlier than that is reconstructed indirectly. Some parts of that reconstruction are extremely strong. We trust them because different lines of evidence point the same way. But as we move closer to the beginning, the confidence changes character. Observation gives way to inference. Inference gives way to theory. Theory gives way to competing frameworks we do not yet know how to test cleanly. Even James Webb, powerful as it is, does not look at the Big Bang itself. What it does is study some of the earliest galaxies and luminous structures ever seen, giving us a better view of what happened after the universe's earliest opaque phases. That matters because the young universe carries fingerprints from whatever initial conditions came first. The beginning is not visible in the ordinary sense. Its consequences are. And that is how cosmology works. It reads the present universe like a fossil record of deeper events.
Scientists still do not know whether the Big Bang marks the absolute beginning of reality, or only the earliest chapter our current models can describe. They do not know whether time is fundamental all the way down, or whether it emerges from something deeper. They do not know whether inflation is the correct account of the universe's earliest expansion, though it remains a leading framework. They do not know whether bounce models, eternal inflation, or quantum gravity scenarios describe anything physically real, because none has yet delivered decisive evidence that closes the case. And the singularity itself remains unresolved. It may represent a true boundary in nature, or it may simply be the place where classical relativity fails, and a more complete quantum theory of gravity has to take over. That uncertainty is not a weakness in cosmology. It is the frontier. The field is strongest where it admits exactly which parts are measured, which parts are inferred, and which parts are still open. So what was there before the Big Bang? The most honest answer is not a dramatic one. We do not know. But that is not the same as having nothing to say. We know the universe was once hotter, denser, and more uniform. We know space has been expanding. We know the early cosmos left behind radiation, chemistry, and structure that still surround us. We know our best classical equations run into a breakdown at the apparent beginning. And we know enough to see that the real mystery is larger than a missing timestamp. Because the question is no longer just what happened first. It is whether first is even the right kind of idea. Maybe the universe had an earlier phase. Maybe our cosmic history emerged from a bounce, a quantum transition, or a larger inflating background. Or maybe the beginning of the universe is the point where our ordinary grammar of time stops fitting the thing it is trying to describe. That is why this subject stays so powerful. It does not just push us back toward the start of the cosmos. It forces us to confront the possibility that reality is not built like a human story, with a clean opening line and a chapter before chapter 1. At the edge of the universe, the real shock is not simply that we lack an answer. It is that the universe may be stranger than the question we started with.
The next step is not farther before the beginning. It is the first era after it that we can actually start to reconstruct in detail how the universe cooled, how the first light broke free, and how the first stars and galaxies turned a nearly uniform cosmos into the structured universe we live inside now.